Welcome, everybody, to this exciting first webinar session in the series that we're kicking off that is called the Energy Innovator Secrets, where my humble self is trying to attempt to find the blueprint to successful energy innovation. And I want to do this by bringing people who are doing this basically as their everyday job, energy innovation, and give them a platform to introduce their innovative products, processes, or services. And then first, basically, we will look at what they do. And then in the second part, I will ask them a bunch of questions to figure out how they do it. And, with the goal to uncover basically, the magic formula to market success with innovation, which I'm sure all my guests would also love to have, right? So, but yeah, anyway, so today we'll be exploring the fascinating world of electrostatic forces and electrostatic motors. It's something that I frankly didn't know anything about before I came across Matt Maroon and C-Motive. And I'm super curious to find out how this tech will help create the next generation of motors. And I can't wait to do this deep dive with Matt Maroon, who's the CEO of C-Motive. Matt is an expert in creating tech that makes our economy more sustainable. And I believe he has a strong passion for solving really tough challenges through the pursuit of finding market fit for new and until that point often unproven technology. And so without further ado, I'd like to give him a warm welcome. Matt Maroon, thank you so much for being here. And
thank you.
Firstly, take a little moment, couple minutes or a minute, introduce yourself to our wonderful audience. And then after that, feel free to dive into this presentation.
Sure.
And just one other thing, we already talked about it, Matt. Anybody has a question, feel free to type it in the chat, and I will feed them to Matt as we go along. So you don't have to wait till later. Matt says he's a pro. He's done this many times. We can't possibly throw him off. So let's any questions you guys have, just let us hear them.
Yeah, I didn't realize I was the first one to run this gauntlet, so I'm a little honored to go first here. Yeah, and as you said, obviously this is part of my job is to tell people about C-Motive, the technology, the products, what we're doing. So please, I don't want to sit here and just talk at the screen for 10 or 15 minutes. I am absolutely happy to take questions along the way. About whatever. I'm not going to guarantee I've got all the answers, but I'm happy to take questions. So a little bit of background about myself. So Lovis, much like you, I didn't know what electrostatic forces or electrostatic motors were until I started here in March of 2020. My background before moving to Madison, Wisconsin, where we're based, was all energy storage or battery startup companies. So I've worked on too many batteries to think about, too many different chemistries. I joke that, I was working on batteries before batteries became cool. So in the early 2000s, no one what would you ever think you would need a battery for? We were using, laptops that were the thickness of library books. You had a battery in your car to turn the car engine over. There was no such thing as a hybrid or an electric vehicle. No one had ever thought of, having battery backup in your house or batteries to, complement solar on your roof. So I got into batteries super early and saw basically 2 or 3 rises and falls of popularity of batteries, right? The popularity of clean tech in general. So I started my career. So I have a degree in mechanical engineering. I am not a very good engineer, which is why I do this is why I talk now, because I was actually a pretty bad engineer. But I got super lucky to get involved as the 3rd employee of a startup company that was looking at advanced lead acid batteries. That was in Illinois, and then moved from there to an advanced materials company in Seattle, Washington, looking at high purity carbon for lithium ion batteries, ultracapacitors, additives for other batteries. Went from there to General Electric, who was doing a startup within GE looking at high temperature sodium nickel chloride batteries for locomotive transportation to utility scale energy storage. I'm not a big company guy, so I couldn't wait to get out of GE as quickly as possible, and then went back to another startup company in Pittsburgh that was a spin out of Carnegie Mellon University. That was, I mean, I have to say C-Motive is my favorite place, but outside of C-Motive, that battery company in Pittsburgh was probably my favorite place. Did a few things on my own after Acqueon, and then found myself here at C-Motive. Because as I'll go into, the thing that most people don't realize is just how important electric motors and generators are to modern society. So if you're in an office or if you're at home right now, there are probably 20 to 30 motors that are just working silently in the background that you never ever think about. So, right, ceiling fans, the fans inside of your laptops, compressors inside air conditioners, the motor that's on my burr grinder for my coffee in the morning. Right, motors they're literally everywhere. They are kind of the foundation of everything we take for granted. And there's over $100 billion of these things sold annually, and no real true innovation for the past 40 or 50 years. So it's been like incremental, small improvements, cost down, and that's just kind of what has been grown to be accepted as a status quo. So that's what I was super interested in when I, first met the two co-founders here at C-Motive, Justin Reed and Dan Ludis. And I started looking at, well, motors aren't particularly cool. It's really kind of hard to, it's hard to raise money for a motor company, but that's until you get just below the surface and realize just how important they are. So that's a bit of my intro, but the intro of the company. So there are a ton of smart people that are the foundation of what we're doing here at C-Motive. I am not one of those smart people, but I am surrounded by people that understand the intimate scientific details of electrical engineering, mechanical engineering, electrochemistry, fluid dynamics, controls. All of those disciplines have to come together to produce the products that we are building today. But it all started with Justin and Dan pictured here on the left. So the two of them were getting their doctorates in electrical engineering from the University of Wisconsin-Madison. They would go to, these seminars that would be put on a monthly basis where big companies would come in, engineers would talk about the research they're doing on electric motors. And as I mentioned, those presentations were talking about, trimming pennies off of the cost of a motor or making tenths of a point of improvement of efficiency. Nothing substantive and nothing, that really is pushing society where we need to go, which is energy efficiency, right? We need to do more with less in general. So Justin and Dan, looking at historically what other motors have been done, they found this concept that Ben Franklin first did 275 years ago. And for whatever reason, right, they were young, didn't know any better, idealistic. They said, man, we could do this. We are going to be the group that finally takes this idea from Ben Franklin, and we are going to be the ones that make it a reality. So they started C-Motive. Two guys in Justin's second bedroom here in Madison, Wisconsin. They moved through a couple different locations. They were literally in a garage at one point in time. It was 2 people, 3 people. And today we are now 18 people. We've got a legitimate facility with a real chemistry lab and a real high voltage lab. And we have kind of finally grown up. And I like to joke when we moved in here, it was like moving out of your parents' basement into your first apartment for the first time, right? It was that level of, wow, we finally made it. So we're currently a team of 18 full-time people. We have a ton of people that have studied this science very specifically at UW-Madison. So Justin, our chief technology officer, has stayed with the company the entirety of since the company was founded. Dan is our part-time chief science officer. In his full-time job, he went back into academia and is a professor at UW-Madison. So a number of the people that work here all earned advanced degrees underneath Dan's tutelage, specifically on electrostatic motors. So it is fair to say that between the people and the intellectual property we have, there is no one else in the world that is like actively researching or developing or commercializing electrostatic motors. If this technology is ever going to see the light of day, it is going to come out of these four walls and with these 18 people. There is no one else doing it. It's kind of crazy to think that there are, I don't know how many, 8 billion people on Earth right now, and there's 18 people that actually know what the hell we're doing here, which is wild.
Well, there'll be like 7 more after today, or
yeah,
10
there you
or
go.
8.
We got 7 more experts that run. Send me your resumes. We'll find you a position. So as I talked earlier, right, I believe that it is a fair statement to say that the foundation of modern society are electric machines. So electric generators, you put mechanical power into them and you get electricity out. So when you think about the electricity that is on the grid, outside of power that is produced by solar photovoltaic, everything else comes out of a rotating machine. So whether that rotating machine is like spun by wind or, marine hydrokinetics, or most likely, you burn coal or natural gas to create steam and you spin a turbine, right? All of that electricity comes out of an traditional electromagnetic generator. Over 50% of the world's electricity, so on the end of that line, over 50% of the world's electricity goes into an electric motor. So again, your coffee pot, your burr grinder, the fan, ceiling fans, compressors, pumps, electric vehicles, everything that you touch has at one point was either built by an electric motor or uses an electric motor as part of it. What we are focused on to begin with is this segment of the world that uses electric motors in industrial and commercial facilities. And the reason why we are focused on that is because if you look inside of a modern industrial facility, as high as 75% of the electricity gets consumed by the building goes into an electric motor. So whether that is, moving boxes or product along conveyor belts, fans, pumps, compressors, robotics, other industrial automation equipment, everything that builds and moves the products that we consume every day is reliant on an electric motor. And again, people have just come to accept that this is just the way it is, right? We just have accepted the status quo of motors for far too long. Market is huge and it's only getting bigger. So $130 billion today globally, projected to double in the next 10 years. This is...
Matt, I was about to say, so in Europe or in Germany specifically, where I'm at right now, there's a huge push to replace conventional heating and cooling systems, or cooling were heat pumps before, but conventional heaters with heat pumps, right? And so there goes probably not one, but several more motors into operation, doing something that previously didn't really require any.
So between that growth in electric vehicles, right, just electrification in general, and most people, when you think of an electric vehicle, right, you think of a Tesla Model 3, but think about all the other vehicles that are on the road that could be electrified. Construction equipment, agricultural equipment, garbage trucks that are running the same route every single day, city buses, all of these things are moving away from diesel and petrol to electrification. It's a huge growth in the electric motor market, let alone all of the other things that as we just continue the trend to electrification are going to need a motor. So of that $130 billion, 99.99% of those motors are built the exact same way with the exact same forces. So I will do my best to explain the science here, but so where people, depending on the questions I get in, I may have to defer. So every traditional motor in the marketplace relies on magnetism to convert electricity into mechanical power. To create that magnetic field inside of the motor, you pass electric current through a bunch of copper windings that creates a magnetic field. That magnetic field interacts with another magnetic field inside of the motor, which is either generated through the same way, passing current through copper windings, or with permanent magnets. Those are kind of the two. There are other things around the periphery, but that's fundamentally how it's done. Create a magnetic field, interact with another magnetic field, voila, you get mechanical power out of it. What we are doing flips that entirely on its head. So instead of passing current through copper windings, we are putting voltage on the surface of these printed circuit board plates. So these are standard, roughly 1 millimeter thick. This is a 25 centimeter diameter standard printed circuit board. It has a number of copper traces on it. And when you put the voltage on the surface of these traces, you create an electric field. And so what we do is we put an electric field on a rotor, which rotates obviously, and a stator, which is stationary. And by manipulating the electric field on the stator, these things interact and the rotor gets dragged along with it. So the corollary here is, I saw the video that you put on LinkedIn, right, advertising it. That was my hair, and you take a balloon and you rub a balloon against your hair, or you rub a balloon against a wool sweater, and you can feel the electric field. You feel the electric charge on the surface of that balloon. That is what we are doing inside of our motors, just scaled up tens of thousands of times to produce the meaningful amounts of torque and power out of our machine. Now here's where the real magic comes in. So the way we are able to magnify that force, that balloon force, up tens of thousands of times, is because we fill our motors with a proprietary fluid. It is a dielectric liquid. It has a certain set of properties, which it's highly insulating. So we can put, pretty high voltages on our plates without having arcs between them, no discharges between the plates. It has another property called permittivity. The higher the permittivity, the greater the electric field strength. And so by manipulating the surface area on the plates, by manipulating the voltage that we put on those traces, and most importantly, by specifically tailoring the properties of the dielectric liquid, we can produce some of the highest torque values out of our motor at very low speeds, which is our, right, that's our sweet spot. That's where we're building our products. These dielectric liquids are commodity organic solvents. They are non-toxic, they're non-carcinogenic. You can procure them anywhere in the world regionally. They can be shipped into Europe or California, so there's no restrictions because of safety or anything else. Low cost, and there are thousands of potential dielectric liquids. And where we have been spending a lot of time and really a lot of brain power and expertise is qualifying the right liquids, and then blending the several together to get the right set of properties that we're looking for. And so, much like a lot of products that we're used to, or the thing that I usually think about is gasoline has various octane levels, and I unfortunately have to put 93 octane in my car because I got a turbocharged 4-cylinder, right? And so you have good, better, best performance on gasoline. You can have the same thing with the dielectric liquids. You can have dielectrics that are good. You could put a better one in there and the torque value will go up, or you could have the best performing one and the torque value is much higher. So we can differentiate our products just by changing out the dielectric liquid that goes inside of the motors.
Hey, Matt, we just got a question in the chat. And I'm not sure if you're going to touch on some of these, but basically the question is for some real world examples. So you mentioned the slow speed, high torque is kind of your speed spot. Do you have some kind of examples showcasing where you excel? Yeah,
absolutely. So I'll talk about them briefly now. I'll hit them later. And then if we've got time, I can pull up some other files to show. So we're focused right now on so we are focused on speeds below 500 RPM. We can deliver full torque and full efficiency from 0 RPM all the way up to that 500 RPM. So where we are putting this technology out to begin with are applications where traditionally you would have a induction motor and a gearbox, or an induction motor and a belt drive system. So those, to begin with, are applications like high volume, low speed fans. We are looking and getting a lot of attention in material conveyance. So conveyor belts, whether those are horizontal conveyor belts or vertical lift systems. And we're also looking at things in kind of the general industrial automation space. So robotics, other sorts of, just use a lot of motors in manufacturing that are doing various jobs. They're almost all needing to be at low speed. And so traditionally that's done with a gearbox, and we can go in and do that in a direct drive fashion.
Very cool. Yeah, I anecdotally, where we used to work out of, the neighbor was working, I forget what the company was called, but they were trying to develop a more low-cost gearbox for robotic arms, and they had been I had no idea how intense it is to design and manufacture those, because you need down to a 1/1000th of precision for them to work. And so if you guys can do it without, potentially that makes a massive savings too in the robot.
Gearboxes are they can be noisy depending on how they're done. They can be pretty inefficient. There are always exceptions. You can spend a lot of money to get a very high efficient, very precise gearbox, but you are going to pay for it. So gearboxes can be noisy, they're inefficient. They need maintenance. You need to deal with the oil or the grease inside of a gearbox. Even gearboxes all leak, you have to deal with, they're kind of a mess. And so going direct drive is the way most manufacturers, most engineers want to go. It is a simpler system. It saves on the OpEx of the gearbox. It saves the CapEx of the gearbox up front. And most importantly, the energy efficiency, which I'll get into, is where the payoff really is for a direct drive motor system. I talked about Ben Franklin. This was what he put together. It was a science fair experiment. He built it to impress the ladies of France, I think is what his real motivation was for putting this thing together. It is 2 Leyden jars. One is positive, one is negative. Some metal thimbles on the ends of glass rods. So the thing will spin, and it's kind of cool, but it can't do a whole lot of practical work. What we're building, obviously very different, right? We've got the benefit of modern material science, the benefit of modern power electronics. We're not using thimbles, we're using printed circuit boards. We're not using Leyden jars, we're using actual power electronics to put the right voltage and the right, AC waves on this rotors and stators. So we've just taken, again, the same concept and really modernized it and made it into a product. So to give everyone a sense, it's 25 centimeters on a square here up front. It's about 20 centimeters in depth, and it weighs about 13 kilos. So it is it's a reasonably low weight, small, compact product for what it's going to deliver. I'll just talk a bit about the product value propositions here real quick. So three main things to keep in mind. First and foremost, no one buys anything unless it's going to save them money, and that's where we start. So a lot of people that are familiar with motors, are confused when I say we're higher efficiency, because they, well, I'm buying a super premium efficiency motor, right? This is the standard in the EU right now, and is going to be the standard in the US in the next 4 to 5 years. 1 kilowatt motor needs to be 85% energy efficiency, but that is at a very specific load point and a very specific speed. Now, by the time you put that motor into the actual application, you have put a number of Band-Aids over it in order to get it to work in the way that you want it to work. So that's what's represented here with these three red bars in this waterfall chart. So first and foremost, you have to actively cool almost every motor in the world. It is the main limiting factor for traditional motors is how do you manage the heat of the system? So you can do that by mounting the motor like in the middle of another airstream. A lot of times there's a fan built on the back of the motor to provide some sort of, convective cooling. There is an efficiency hit that is not free to provide that active cooling. Every engineer that I know, if you need 1 kilowatt, you don't spec a 1 kilowatt motor, you're going to spec a 1.5 or a 2 kilowatt motor, right? You do that because that's what we were all taught in school to add a factor of safety, but also because you're trying to manage the thermal load. So if you put a bigger motor in, the amount of current that you're passing through the machine relative to the size of the motor, right, means you're gonna heat up less. And so this upsizing a motor is really intended to manage the thermal load on the machine. Knock off another 8 to 10 basis points on the efficiency for that. And then lastly, the gearbox or a belt pulley system is where you see a ton of efficiency losses. So in a fan application or in a conveyor belt application, where you're taking a traditional motor that spins at 1800 RPM, 2000, maybe 3000 RPM, and you need to gear it down to 100, maybe 200 RPM, that 10-to-1 or 20-to-1 gearbox is going to take another 15 to 25 points off the efficiency. So when you look at the full net system efficiency, electricity into the motor, to the actual, shaft power out of it, these industrial applications are seeing anywhere from 50 to 60% net efficiency. And so this is what we're going in to replace. Instead of needing active cooling, instead of oversizing the motor, instead of using a gearbox, well, we are building our machines that will go direct drive, deliver full torque from 0 RPM, deliver full efficiency from 0 RPM, and get rid of all these extraneous sort of components that you need in a traditional system. So you're actually moving from 55 to 90+% efficiency. This picture is the proof. So what we have here are two comparably sized motors. We're not cheating and having a real small electromagnetic motor and a really big electrostatic machine. These are rated the same motor. They are doing a tug of war contest against each other. So the two shafts are tied together. We are running these at 200 RPM at 4 Newton meters. And what you see in this thermal camera image after an hour is everything that I just talked about. The traditional motor, in order to continue to produce that torque, needs to continuously pass electric current through the copper windings. Ohm's law takes over, right? You have resistive heating because you can never pass anything without any resistance whatsoever. Despite what, anyway, you can never get around Ohm's law. And so that traditional motor, over the course of an hour, the temperature rises 26 degrees centigrade. Again, for us, because we're not passing current through the system, we're putting voltage on the surface of the plates, there simply is not the same amount of thermal gains. There's not the efficiency loss. In motors, heat is a proxy for efficiency. So this is the picture worth 1,000 words sort of deal. The second value proposition really comes down to supply chain and raw materials. So, there's no magnetism in our motor. We're using 90% less copper, maybe 95% less copper in our machines. There's no electrical steel. When you look at where these critical materials come from, they are not sourced in North America. They are not sourced in Europe. 90% of the world's permanent magnet supply comes out of China. And I think it is reasonable to say that, like, geopolitically, there's no guarantee that we are going to continue to have, secure supply chain out of some of these countries. So there is a big question of just pure availability of high performance materials that you need for higher performing motors. The costs separately continue to rise, right? As we move to a more electrified world, copper is going to become more and more of a precious material. No matter how much copper we have, if you are electrifying everything, if you are putting in electric vehicle charging stations in everyone's garage and everyone's parking deck, we are simply going to use a ton more copper than we're using now.
Yeah.
Prices have gone up, and they're going to continue to go up.
I saw Matt, I saw a chart, and I mean, it might have been hyperbolic, but something like over the next 10 years, the copper mining has to increase by 1,000% just to keep up with like projected demand, which I don't even, I mean, typically human ingenuity has always led to, discovering and being able to mine more and more resources, but
Yes.
but at the end of the day, it's finite at some point, right? I mean, or there's a diminishing return fact where it's like, well, it's so expensive now, we just simply can't
Right.
use it for this, but we can still use it for that type thing.
Yep.
So
I mean, that's the bet that we're making here, right? And that's what a lot of people we talk to are concerned about. So, when we talk to motor manufacturers, a lot of them are just trying to hedge their bets against, well, what if the worst case comes true? What if copper does double or triple in price? The market is only going to sustain so much of that cost. You can only pass down so many costs to consumers before they just give.
Right.
We've seen that with motor prices in the past couple of years. Motor prices continue to tick higher and higher. And it's not because these companies are making greater and greater profits. It's because their raw material costs have continued to rise over time. And that's true with copper. It's very true with the electrical steel that goes into some certain types of motors where you're using, I'm dropping the word, but all of these materials go up. And unfortunately, we have really centered the production of these in just a few certain geographies. Let's bring this to actual numbers. So we didn't pick Germany because you're in Germany. We use this as the example because these are really the two ends of the spectrum. So here in Wisconsin, unfortunately, a lot of our electricity is still sourced from coal here. So very high carbon intensity, relatively low energy costs. I think we're at 14, 15 cents per kilowatt hour at the residential level, probably 11, 12 cents a kilowatt hour at the industrial level. Germany, on the other hand, or the UK, or a lot of other places in the Northeast United States or California, kind of completely the opposite. So very low carbon intensity because there's a much higher preponderance of renewables and solar. But the energy costs are significantly higher, right? 25, 30, 35 euro cents a kilowatt hour is not an unheard of electricity price. So if I have a fan in my manufacturing facility and I turn it on and I just never turn it off, here in Wisconsin, that fan is going to cost $800 to run a year. In Germany, that could be over $4,600, just a fan, right? The thing that just sits in the corner, you never ever think about the fan running. It costs a ton of money to actually just let that thing run. In this case, the assumption we're making here for the traditional motor, it's a traditional motor, induction motor, belt pulley system, and you've got a net energy efficiency of 60, 65%. The C-motive equivalent here, you put our motor on the back of that fan, direct drive, run it at 90% energy efficiency. And whether you're in Wisconsin or Germany, right, we're still saving 60, 65% on the cost. There are so many things that we take for granted that if you really looked at what the energy efficiency was, you would say, well, this is crazy. Why do I continue to do it this way? A lot of our customers are actually interested on the left-hand side of these two charts. So more and more companies have made sustainability commitments to their shareholders, to Wall Street, and they have to report back what they're doing about carbon emissions. And so if you use less electricity, you obviously can take credit for the avoided carbon savings. This is what happened when everyone moved to LED lighting within the last 10 years, right? It was a natural, why wouldn't I? It saves money. I get credit on my sustainability commitments. We believe that motors are kind of the next version of LED lighting. It's just a no-brainer. If you're going to save money and you can help or meet your commitments to your shareholders, why would you not do it? So that's where we end up. What we're building, direct drive, when you look at the system level cost, we are a comparable system level cost because we're replacing, a motor, a gearbox, an active cooling system, et cetera. We're delivering 35% plus improved system efficiency, and the payback that we're looking at here is anywhere from 1 to 2 years. The supply chain side of things, so whether you're a motor manufacturer yourself or you're a system integrator that relies on motors as part of a core component of your product, you have to be worried about availability of the right raw materials and the right motors in the long run. So we provide a fully regionalized supply chain. We can build everything we need for our motors can be produced right here in the Midwest. The same thing if we had a plant in Germany or in California or in South America, right? Everything can be procured regionally. You're not reliant on, critical raw materials from a sole source.
And
lastly, the carbon savings continues to drive, where investment is going. It continues to drive the strategy for major corporations. And there's only so much solar you can put on roofs. There's only so many wind wrecks you can buy. There's only so many light bulbs you can change out. We believe that motors are the next way to save a lot of these sustainability. And so,
Matt, and for general scalability of the production. So if I imagine there's no copper windings in there, that means the geometry of things that need to be machined to make these motors is also much simpler, right? So
yeah.
so that it sounds to me like it's actually more easily scalable to make a lot of these quickly.
This is a pick and place operation, and so that's actually a really good segue to this. So we're a technology company. We're focused on the topology of the motor itself, the power electronics, the liquid. We are not going to manufacture this in the long run. We're not going to raise $100 million, set up our own manufacturing facility. We are actively looking for contract manufacturing, licensed partners that will take this and build it themselves. The manufacturing of this is you procure the printed circuit boards, you have the hard goods, the metal components, cast to size, and it's a pick and place operation of these plates. They just get stacked up. So the current motors we're building use 15 of these plates just stacked up on the shaft. Motor gets filled with the liquid and you're good to go. So we're looking to make partnerships. We're currently putting demo units out in the field right now. So if there's anyone that is watching now or watching later that's like, hey, I've got a ton of motors for fans in my facility or conveyor belts. We are looking for demo partners to get this stuff out of our labs, get this stuff out in the field. Let's generate some real world data. Let's do some mutual learning. Let's look at pilot projects. And then let's talk about scaling from there. So we want to start product family today is in the 20 to 150 Newton meter range. Because again, we talk about torque and not really power. But these are kind of 1 to 3 kilowatt or 1 to 4 horsepower units. In the future, as we grow up, get bigger, become successful, the intent is that this motor technology can be adapted to go into electric vehicles, renewable generation, marine propulsion. There is a huge array of applications, but we want to crawl before we walk, before we run. And so that's why we're really focused today on finding some partnerships, finding some early technology adopters in industrial applications so that we can prove this out.
Is there, so there was a question here again from the audience, which I'm gonna, it's actually a similar one I wanted to ask.
Yeah.
So it says, so with ongoing advancements in technology, is there, what is the most exciting future application or more future developments that you guys are looking for? And so what was on my mind was, I don't know if you follow this at all, but you're probably too busy to be on Twitter, but there's this Korean paper about a room temperature superconductor. Does that make your motors better or worse or?
So I'll answer, let me do the two questions. First, the most exciting application for me will be in renewable generation. So before coming here, I was working for a renewable development company. We were doing utility scale solar and energy storage, but a lot of my colleagues came out of the wind industry. And when you look at what goes into a wind turbine, wind turbine blades spin at 8, maybe 10 RPM. So either they have, a huge gearbox on them, which has its own efficiency losses along the way, or there will literally be a metric ton of permanent magnets of rare earth metals inside of a direct drive. I think that that is a huge opportunity for us. We could go in, do direct drive, no permanent magnets, right? Very little copper, and deliver 97% generation efficiency. That is only going to continue to drive down the levelized cost of energy for wind. It will only continue to make, offshore wind more viable. So I personally am excited about renewable generation, but I'm not so naive to think that we can go out and build a 2 megawatt, generator tomorrow, right? It is going to take a decade to get there, and it will take time to make sure that we have the data to make, for a bankable solution. But I think long-term, that is the most exciting part of this technology, because we are never going to go back, no matter what people think, we're never going to go back to coal. And at some point, we're not going back to natural gas. The future will be renewable. And so the more efficient we can make renewable, the better off we're going to be. With respect to the superconductor, doesn't impact our motor at all, because again, we're not passing a lot of current through our machine. We're talking about milliamps in our motor, whereas a traditional motor is, amps or tens of amps. I think first off, it would be amazing if they're able to replicate that result and make it scalable. But we all know, it takes a ton of work, and most importantly, a ton of money to go from a paper to a product. And so I hope they're successful, because it would make so many things so much better, right? Can you imagine if we could, as we continue to need to build more transmission and distribution lines on the grid to move renewable energy across countries and across continents, superconducting materials would be great. I think there's more important places for superconducting metals than in traditional motors. I think those will be the last things that ever see that technology, but I hope it works out. I'm always a fan of super cool stuff that could help out, kind of at this society level. So I hope they're able to replicate it. I hope someone adopts it and takes it to production. It would be great.
Yeah, for sure. I'm hopeful for the same. It's just been fun to see the excitement. It's not so often that people get really excited about some nerdy physics stuff.
Yeah.
So that's already cool. Very good, Matt. Super in-depth presentation.
Yeah.
And you've answered some of the questions that I have already. And of course, audience, if there's more, feel free to post them here. Do you know, so as you said, you're not one of the two founders originally, and you've talked about the story with Ben Franklin's invention to impress the ladies of France. But beyond that, do you know what was the kind of inspiration? Was there another inspiration, let's say, for the founders to go look at this?
So Dan, our chief science officer, Dan is Dan's a big movie buff. He loves movies. He loves science fiction. He loves all that stuff. And so Dan has always been curious about things you see in movies so one of his favorite movies is Back to the Future, right? And the flux capacitor and all that other sort of stuff. So Dan has this natural fascination with capacitors, and our technology is, it is a rotating capacitor is what it is, right? We're building capacitance between the plates, and that's what's generating the thing. So I don't know if that was inspiration for Dan, but he loves coming up with these most weird little tiny corner of the universe esoteric ideas and then seeing if they work. And that's where it was. He told me this the other day. So in The Hunt for Red October, the engine drive that's in the silent submarine that the USSR has they call it the Caterpillar. It's an electrostatic drive. And so way. So I don't know how he pulls together all these weird scientific principles in movies, and he operates on a different level than the rest of us do. So I think I think it was truly just like natural inspiration.
Yeah.
And then he and Justin were just young, and like, you remember when you're young, you think you can do everything, right? The world, everything is possible. And so like
Yeah.
that energy is contagious. And man, Justin is stubborn and he never gives up. And here we are, right? It took the
Perfect. Yeah.
crazy idea and the stubbornness of the two of them to get together to make this thing happen.
That's awesome. Yeah. Well, so now I have lots of questions about the hunt on Red October, but that's we'll
I am
table
not
those.
the right guy for that.
But I mean, so the inspiration strikes, right? And then, so this is kind of my second question, but you've already answered it quite amply. You know, how was the need, I guess, identified for the product? But it's, once you look into it, it's obvious. So with
Yeah.
with the lack of innovation in the last, yeah, what, century, basically, in
Yeah.
electric motors and everything that you've explained.
Yeah.
So so ever since you've joined, what would you, from your perspective, what is the hardest part of creating this product?
Everything.
Is it like, can you categorize
Well,
it as like the tech? Is it finding the customers? Is it like how to explain the science? Or
there are two things that are really difficult. One is convincing people that this is super important to have, particularly the investment community. So, the investment community goes through whatever fad it's on and dumps a whole lot of money in there. So, we saw clean tech continues to be relatively strong. There was a ton of money dumped into crypto. There's been a ton of money dumped into AI. There's been a ton of money dumped into every single app that you can imagine that's being developed. But how do you convince people that, my assertion that motors are the foundation of everything we take for granted, right? You really got to get someone's attention, and they really got to think about it, because it's not the flashiest thing to talk about, right? It's not you don't go to a party and say, hey, I made an investment in electric motors. So, what the challenge we've had is like attracting the right sort of investment. And then now that we have, and we've got some very great investors behind us, we got to prove that the market wants what we have. So now the next step of convincing is all those engineers out in the world that have been buying the same damn thing for 20 years or 30 years, right? How do you convince that engineer that sat at the same desk for 20 years to do something different, to take a risk on this, right? And so the hardest part of not just C-Motive, but every hardware startup is convincing someone to do something new. And that's what, no matter what the technology risks, you get enough smart people in a room, they can figure this out, right? You can work your way through, human ingenuity can work your way through any scientific problem that you have if you've got time, patience, and the right people. But changing mindsets and changing how people think about the thing that they have taken for granted is so hard, right? The science of selling and the science of that application is just, it's very, really, really difficult.
so as a segue to that, so I mean, so my advice would be, right, I find the people that have a huge problem and help them solve it. But
Yes.
but how do you find that target market, I guess, for your product?
So right now, our focus is our approach to getting that sort of buy-in is we are going to the big end users, the sustainability groups at the big companies that have made commitments to Wall Street that they are going to cut carbon emissions. So directors of sustainability at companies like automotive companies or FedEx, DHL, the United States Postal Service, General Motors, GE, Amazon, all of those companies have commitments. They are the ones that have the problem. Their problem is, how am I going to get credit for avoided carbon emissions? And that's the problem that we're trying to solve. So we are actively seeking out a lot of those people, and then those people help make the introductions for us to the engineers and to the equipment manufacturers, right? And they say, hey, I'm not going to buy your conveyor belts or your fan or whatever it is if you're using a motor that's only 50% efficient. I want an electrostatic motor at 90% efficient. So that's how we're trying to, change hearts and minds, is by going to the end users that have the problem and then having them pull us through their supply chains.
Yeah, that's smart. So it becomes more of they're being told to design that way rather than them deciding to
Yes.
design that way.
So if we can get spec'd in from the beginning, we are in a much better position. Yes.
Yeah, of course. But I assume that, I mean, that's still not easy to achieve, right? But
Right. It is not
it's
easy. If it were easy, it'd be done already. Yeah.
right. Yeah, but it's for sure a good approach. Um, when C-Motive got started, I assume, like, I guess, how much of this journey was like apparent to the founders? Did they have any idea it was going to come this far or go
No.
this route?
You never know. You never like, yeah, I think there's still, you learn something new every day. I think, you know, you never think it's going to be easy, but when you look at the twists and turns along the way, even since I've been here, we've had 2 or 3 different pivots on different applications, different types of customers, different, you never know what it's going to be. You never know what to expect. Both of the co-founders are first-time entrepreneurs, so they were coming into this, you know, with enthusiasm and with a lot of intelligence and a lot of like stuff, but yeah, you just got to roll with the punches, man. I think that being adaptable and being able to think on your feet and move and make a decision, I think, are the biggest things that have to be done.
So got another interesting question from a guy who identified as a recent graduate student. So he said, you've talked about how this technology requires bigger facilities to manufacture. I'm not sure if that's actually what he said, but we'll keep it as that. But when I was in school, we made the normal motors as an experiment. So I assume they wound some coils and stuff. What C-Motive is doing, can that be replicated so that students could get their hands on the tech and kind of learn by doing how to use it, how they work?
That's a great idea. You know, later, sure. It's right now, you know, because honestly, we're still developing stuff, right? We are still learning things every day. I don't have a recipe that we could hand it off, but that's the goal, is that we will come up with the recipe, the size, the shape, the drawing package, to be able to hand it to other manufacturers to make. I suppose that could be like, you could envision a world where that could be done in a kit, where you could like do that in school. There were some power electronics stuff to worry about, but yeah, it's why we do, when we talk about the experiments, that's why we talk about the balloon stuff, right? It's the easiest way to explain it to somebody, particularly students, is like, here's the force, right? Rub a balloon against your shirt, put some confetti on the table, and you can experience it.
So one thing that you just touched on slightly, I forgot to ask about earlier, so with I guess the nice thing with a conventional motor is, since it is so simple, usually you can connect it to a power source and it'll start spinning without any control, right? No RPM control or anything. Is it still that simple with an electric static motor, or does it need like a more sophisticated control to get it to do something?
So we're also building the power electronics, the drive that sits between the wall and the motor itself. So every motor in the world has a drive, whether it's embedded in the motor or, you know, it's a separate device. The applications that we're focused on to begin with need a little bit more control. Believe it or not, even fans need a little bit more control than like your coffee grinder or something that simple. So we're focused on things where, yes, we will build the drive. It'll be part of the overall package. So it'll be a drive and a motor, and it will have the controls embedded in it to, you know, manage to speed, manage to torque, all the right feedback loops, et cetera. So we do have to do the same thing. It's not any more complicated. It's just different because we're now doing the electrostatic instead of electromagnetic motors.
Yeah, it makes sense. So you mentioned that you guys have pivoted around different approaches and different kind of applications. If you had to define the 3 simple steps, your best approach to product innovation, and maybe you can you know, what do you call that, orient around the pivots that you guys have done, but what will be your best 3 to 5 steps to do successful product innovation?
Oh man, I think first and foremost, like, you should go where the data takes you. Like, you do a bunch of experiments in the lab. If you find one direction that works, like go that direction. Don't try to fight it. Don't try to fight physics and try to do something so much more complicated. All startups and all like product management is a give and take between the market, between the commercial team and the technical team. Oftentimes the commercial team just needs to know what to tell customers and what they can sell, and they can go out and find people that want what you have. Too many times it seems like a technical team will get data goes in one direction, and then they're like, well, that's interesting result, but we need to focus on, this other thing. And they're like, so I think in general, take the path of least resistance. If you get good results going in a certain direction with a certain motor size or certain number of plates or whatever the case may be, do that, and then go look for customers where that solves a problem, instead of sometimes the other way around, which is technology development's really hard. And so why make it harder on yourself? So path of least resistance. I think, the other things are the standard that you hear from everybody, right? Like actually talk to customers and listen to them. If they say they don't care about energy efficiency, don't force them. Don't force her. Like we've talked to companies that say energy efficiency isn't a problem. Cool, man. I'm not going to call you back. That's no problem. Like we'll go find somebody else, right? Again, it's really just like listening and following that path of least resistance. There are people that want what you have. Sometimes it just takes longer to find them, but they are generally out there.
Right. Yeah. I'd agree wholeheartedly. Many times, been in a situation where the company was like very in love with their solution, which is rather than what the customer needs, right? So, and there's a feel of tension that's healthy to some degree, but if you keep going, it's like no, but this is so cool, eventually they'll get it, and like they might not. You might run out of cash before they get it.
One of my best friends, his ears probably perked up, because that is that's the thing that he always talks about, right? That when you get technologists that love their technology too much, you are blind to what anyone cares about. And the only thing you should care about is, will someone pay me for the thing that I'm building? And if no one's going to pay you for it, what's the point?
Yeah, for sure. So this is a question we also got from the audience, but I also had it on my sheet very similarly. So let's say, what advice would you give to others that are wanting to invent and innovate in the energy space in general? So think, first-time entrepreneurs or maybe serial entrepreneurs that want to get into the industry. What would you say? What's your one best thing to keep in mind if they want to get into that?
Work with people you like. Life is too short to not want to go into the office or not want to talk to certain people, on your team or at the company. So I think finding your tribe, so to speak, and like sticking with them, I think is the biggest thing, because this is hard enough as it is. Again, it all comes back to why make it harder on yourself, right? You're both technically, commercially, and then personally. So find something you care about and find people you like to work with. And I think that solves 90% of the problems about how do I really get into this and how do I keep plugging away even through the tough times.
100% agree. Yeah, many partnerships. I mean, well, so I was in a position where I talked to essentially like a VC fund, and they said, the most common reason companies fail is founder breakup.
Yeah,
it's not anything to do with the tech. It's got nothing to do with product market fit. It's just you start with somebody and they end up not liking each other anymore, and then they're like, "No, let's just shut it down." That's it.
Like, so the world would be such a better place if we just don't be a jerk. Just be like, yeah. That's so anyway, that's how we're trying to build C-Motive. We got people that care about what we're doing. Yeah. Obviously talented and smart, but we all try to get along, and that's really makes a big difference.
That's really cool, Matt. Hey, we are just at the top of the hour.
Yep.
I thought this was going to be 30 to 40 minutes, but that's why it's good that we did reserve the whole hour. I appreciate you so much and the energy you brought to this presentation. I've genuinely learned something about electrostatic motors and C-Motive. And yeah, just thank you for taking the time and
Awesome.
hanging
All right.
out with us today.
Yeah. Thank you very much.